Distillation in UNBC Northwest's public presentation series. And today we're glad to welcome one of our regular presenters, Dr. John Krisinger from Northwest Community College. If you'll remember last year, he gave a very popular talk on the importance and value of vitamin D supplements. And my wife and I now have tripled our regular dose thanks to his advice. So a lot of good information here in the area of biochemistry and pharmacology, which is Dr. Krisinger's specialty. He teaches in the nursing program there, covering areas as diverse as physiology and anatomy and pharmacology and pathology even. So today I think he's pursuing maybe something that is more of a hobby with this look at the history and chemistry of the alcoholic beverage. So John, I'll let you take it away from here.
Well, there's some of my science in there too, because I will make some reference to alcohol as a drug that humans use. So anyway, I think I don't need to stress this. I was going to tell you, you sent me an email and I sent you my presentation, but Alex has put it already on the UNBC website, so you can find it there and download it. So I want to talk about the alcoholic beverage in general. I gave a lecture just on beer where I had a lot more time for details, so here the details have to be sacrificed. I want to talk about beer, wine, and then also about the distillation products people use, and finish off with a few medical social issues around alcohol. So the alcoholic beverages probably come about by accident. In fact, we see that in animals too, that occasionally fruits are fermenting on their own and then they contain alcohol and animals eat them, and probably that happened to our species too, except we have the brains then to realize that and interfere and make the best out of that. So the first beverage probably was from a fruit, most likely wine. In fact, with today's analytical science, people were able to find pottery in China that dated actually by carbon dating around 7,000 years. And they found chemical traces that point that an alcoholic beverage was stored in there. Of course, you wouldn't find ethanol in those artifacts. Ethanol is far too volatile, so it would be long gone. But in the analysis, they found evidence of chemicals that were soaked into the material that point at grapes, hawthorn berries, honey, and rice. And in fact, that was published a while ago in the Proceedings of the National Academy of Science, a very prestigious journal. And so anyway, around that time also barley has been used and grape wine were made in the beginning. And all of this took place at first in the Middle East of all places. So the earliest evidence of wine production then, other than this, is 5,400 BC in Iran. And then there are literature evidence that pointing at the existence of alcohol, mainly used in medicinal and ceremonial procedures in Sumerian and Egyptian texts, dating about 2,100 BC. And then there's interesting references in scripture. For example, in the Hebrew Bible, speaks about alcoholic drink to give those who are dying and depressed. In fact, here's the actual verbatim quote. So give strong drink to him who is perishing, and wine to those in bitter distress. Let them drink and forget their poverty and remember their misery no more. So they know how to use this drink. Another quote from the Psalm says, so that they may bring forth fruit from the earth. Food from the earth, obviously they were looking at the production, what you can eat, and wine that makes man's heart glad. And then since it's actually only 11 o'clock, is it not, right? Because we are fooling around with the time. In fact, as my grandfather's free shopping, that's when some people that are retired have their first drink. Anyway, in the New Testament, there's an interesting line where people are speaking in different languages and still understand each other, and somebody says, oh, they're all drunk. And then someone says, these people are not drunk, as you suppose. It's only 9 o'clock in the morning. So maybe that's the first evidence of the 5 o'clock rule that is so well known. Anyway, now the beer history. Before 6,000 BC, beer was made in Sumer and Babylonia, so again in southeastern Europe and the Middle East. There are actually reliefs that are in existence in Egyptian tombs where the process of beer making is demonstrated in pictures. So it dates back to 2400 BC. And then the technique was brought over to Europe from the Middle East, and again there are historical references to beer by the historian Pliny and Tacitus, now in our area, AD, where they talk about my ancestors in Northern Europe, the Saxons, Celts, and Nordic, are said there to drink ale rather than wine, like what the Romans did. In fact, many of the terms that are used in beer brewing come from the Anglo-Saxon language, like malt, mash, wort, and ale are all from this era. So then fast forward to the Middle Ages. Oops, that went too fast here. So during the Middle Ages then, the monastics were getting into making beer, wine, and cheeses. We have to remember monks were very religious people. They prayed a lot, but they didn't live off alms that they received. They worked. They produced stuff that they could sell. And so beer, wine was one of their fortes. And no wonder our local brewery actually chose a monk as the mascot of the brewery. Although I highly doubt that back in the Middle Ages they would have backcountry skis on their back like this fellow actually has. He has a new version now where there's a fishing rod in the back. So then during the Middle Ages, beer was quite different, as you can imagine. Anything we do as humans becomes more and more refined and sophisticated. So the earliest beer were probably very different from what we have now. Certainly they were a lot lower in strength of alcohol. And if it tells us anything, there are documents that reference to nuns being allowed, how many pints was it? 6 pints of ale each day. That would amount to 8 conventional sizes of beers. Anyway, so cider was made from apples, and then pomace is an interesting concoction. All sort of stuff was used when people made wine. The leftover skins, they still have enough material that you could make alcohol from it, and that was one way of making alcohol for people that were not as well off. So typically real grape wine, as we know today, was more the drink of the more well-to-do people in those days. Now, of course, the monastics have made a big lasting effect on beer brewing. In fact, the Benedictines in today's Germany, in southern Germany, in Bavaria, that brewery was founded in 725. It must have been closed at one point or another. It's in continuous operations since 1040. So I might still be around for the 1000th anniversary of that place. And actually, this is the German commercial. It says, "Thirst to life and the origin of beer." And a while ago, when actually Pope Francis was elected, a German classmate sent me those 2 pictures, and he said, "I knew I'd seen them before." And that's actually a coaster from a brewery in Munich. So obviously, again, it's a monastic beer, and the fellow really looks very similar, doesn't he? And certainly not from Argentina. So now, where does this lovely spirit come from? It's funny, the word spirit obviously comes from the fact that normally if you drink hot chocolate or water, there's nothing happen to your head. And people knew there's something funny that is in those drinks that enlightens the spirit. So, and of course, we know now it's the yeast. So yeast is a unicellular fungus, and they may reproduce by fission. So they simply divide in 2, like most cells do. Or the particular one we use to make alcohol are budding yeast. And what that means, you can tell here, this cell is the parent cell, and it grows the daughter cell as a continuously enlarging bud until it has the same size of the parent cell, and now we have 2 cells. So hence the name budding yeast. In fact, the technical name of this organism is Saccharomyces cerevisiae. Obviously, that's where the word cerevista comes from, as beer. And saccharose actually means sugar. Saccharose, we use that word. And myces, or mycology, is the study of fungi. So hence the name. And of course, this has nothing to do with Budweiser, the budding yeast. That's just a coincidence. I could tell you more about the struggle of that name, Budweiser. So then, how does this alcohol get made? Many plants store energy for the next generation in the form of carbohydrates. Not like us, we store it as fat. So, and those carbohydrates, either in fruits, they're sugars, or in grains, they would be starches. And they can be used to make ethanol. And it's done in fermentation. The word fermentation refers to metabolism when you don't have enough oxygen. So naturally, if you just have a big bucket and you throw all kinds of fruits in there and mash it up, it is an anaerobic environment because only the surface has access to air. And if a bucket is about this tall, the lower layers see no oxygen. So you basically, with very non-sophisticated methods, you will have a fermentation going on for the most part. The yeast then produces alcohol, and obviously the alcohol can't really go nowhere, so it will be increasing in concentration until it becomes lethal to the yeast. Some strains die at 10%, some last till 18%, but that's it. You couldn't make hard liquor with fermentation because they kill themselves. So then the fermentation is an interesting process. Glucose is a sugar of 6 carbons, and in a very simple line of reactions is broken in half. So you can do the math. Pyruvate is then a compound of 3 carbons. So it's literally broken in half. The process gives a little bit of energy. As you might remember from high school, ATP is the energy molecule of cells. So you get a little bit of energy and you have broken it in half. Normally, when there's oxygen available, metabolism carries on. And what the yeast then does, it grabs the pyruvate, oxidizes in one step. So here's the next 2 carbons leaving, or the first one's as CO2. So then if you do the math, if pyruvate has 3 carbons, if I'm losing 1 CO2, I make a molecule of 2 carbons called acetyl. It's an acetyl group hooked up to coenzyme A, and that is then completely oxidized in what's called the Krebs cycle, or in aerobic metabolism, and then all 6 carbons of the glucose will end up as CO2. And the yeast will get lots of energy. The measly 2 ATP here are dwarfed compared to 34 ATP you get under aerobic conditions. So the yeast really would love to have oxygen, but the brewer doesn't give it to it. So then, if there's no oxygen, the yeast has a problem. What the yeast then has to do, the yeast cannot keep running glycolysis unless it regenerates this little cofactor called NAD+. So it will be stuck. Then an emergency fix for the yeast is, well, I'm taking the pyruvate and I'm making it into ethanol. And the only reason why it does that is because it regenerates the NAD+ so it can keep eating the sugar. But it's a very lousy process because, well, you make no mass ATP here because you can't run it. And also, as a symbol of how wasteful it is, consider this. Glucose contains 4 calories per gram. The ethanol that's made contains 7 calories per gram. So there's a lot of energy in the ethanol, which the yeast can't use. It's waste. By the way, you do the same thing if you're running your muscles at maximum force. They will start lactic acid fermentation. So we have a different emergency fix than the yeast. Wouldn't that be funny? If we would do the same thing in our anaerobic condition, you would get drunk as you sprint. So we won't. So anyway, I'm making a little pun here. So in the eyes of the yeast, it's wasted. That alcohol is wasted in terms of energy, but that's what it does. So now let me first look at the history of wine. So wild grapes are found again in warm places on the earth. So mainly started to be used in the Middle East once more, and then in human history, always multiple things come together. When people were able to make vessels that you could actually ferment something or keep juices in, there was a prerequisite and also then the sedentary lifestyle of agriculture allowed people to domesticate all sorts of plants, including then grapes. So that made wine production possible, and there's evidence dating back to 6000 BC in Georgia, obviously not the Georgia in the United States. So then there was widespread use in the ancient world as beverage, medicine, ceremonial drink. Let me just tell you already now, until the Industrial Revolution, humans never made large amounts of alcohol. It was all fairly low key compared to what we do now. Very interesting, the same is true for smoking. Humans never smoked much until the Americans invented the industrial production of cigarettes. Then it takes off, and then we have all this cancer. So it's a typical thing of humans. When we do things in excess, we create new problems. So in those days then, wine was found in warmer latitudes. Generally between 30 and 50 degree latitude is the ideal climate for grapes to grow. So we would be excluded from this, well, my native Germany, well, at least the northern part wouldn't work. So in the north then, people would rather make beer instead of wine. So also then, wine became, of course, a material that was needed in the Catholic Church, which of course dates back 2,000 years, and it was a reason that somebody should look after, keep making wine. So again, the monastic people were heavily involved, so the Benedictines were the largest producer of wine at that time in Europe. Vineyards with famous names that we recognize in Champagne, Burgundy, etc. I put my little reminder here. This is way back before we had Germany and France as a country. So those countries as we know them today, they were actually not founded that long ago. So technically, that's even a wrong number. The Federal Republic of Germany was actually formed after World War II. So anyway, this was all done in the history before we actually had France and Germany. So then, in fact, today's Germany used to be for 800 years the Holy Roman Empire with, what's his name, Charlemagne. He was one of the first ones, if not the founder. I don't know too much about history. But anyway, they were heavily involved in the wine culture in that time. A little interesting, fast forward in the history, I don't know how many of you are aware of the problem. Again, humans travel around and they cause problems with exotic species. So the great French wine blight, there was a severe infestation with a pest, an aphid that almost destroyed all vineyards in France and neighboring countries in Europe. And it's caused by this aphid. I don't want to try to pronounce this critter. And it was brought to Europe by ship from the Americas, from North America. So, and that has led to the fact that nearly all grapes that are grown in the world, with the exception of some vineyards in Chile and South Australia, are use grafting. So basically what they have the American root system and then grafted on top other European, mainly French or German grapes. So this grafting technique was invented thousands of years ago. People didn't worry about how it works or why it works, but it works. They tried. Obviously, if you try to transplant organs in animals, that doesn't work as well as it does in plants. So in horticulture, this was done for a long time, and it solved the crisis of the wine industry in Europe. So basically, the underground is the stalk, so that's the American root, and then the above ground called the scion is basically the word for shoot. So the shoot is then coming from all sorts of selected grapes, and that solved the problems of this blight. Anyway, here's a picture of how the grafting was done with little fabrics, and here's one of the areas close to where I grew up. This is a river that goes into the Rhine. This is, of course, a very large river with lots of vineyards, and there's smaller tributaries. In this case, the Romans occupied this area about 2,000 years ago, and they started growing wine and brought some culture to those wild Germanic people. So now, how do we make wine? Obviously, we all know there's white, there's red, and there's rosé wine. So what's the difference? It's actually very interesting. if you simply crush grapes, whether they are almost colorless or very dark skin, the juice is colorless. The color is in the skins. So then white wine is made by any grape, if you wish, and you immediately separate the skins from the juice and then let it ferment. It's fermented at a relatively cool temperature and you get white wine. So you can make white wine actually from grapes like Riesling or Gewürztraminer or Pinot Noir. If you wish, you can make white wine from all of them. Now red wines then, there are hundreds of varieties used worldwide. What we do here, you leave the crushed skins with the juice while it's fermenting. And it's also done at a much higher temperature. And now the alcohol that forms will start dissolving materials not only from the skins, but also from the seeds. And that causes now a very different wine to form. The color comes from chemicals called anthocyanins, and then the seeds contain phenolic compounds that give it an astringent effect to tan animal protein at the height. It's also used as phenols, and that's where the word tannin comes from. So tannins would not be present in white wine then. And then the rosé would be an intermediate. In rosé, you have to crush, of course, a colored grape and leave the skins for some time during the fermentation. So you have some pigment extracted, maybe for 1 to 3 days. You can play with this and make it darker or less dark. And voila, we have 3 different types of wine. So now the modern wine production, obviously, like I mentioned, people have become very sophisticated in anything we do. And I'm making a little bold statement here. I know we have some wine connoisseurs here who probably know a lot more than me about it. I'm making a statement here. Wine starts from grape juice. At that level, it's a simple beginning. And then it gets very complicated and complex to fine-tune what ultimately is coming out of this as wine. For example, the time of harvest, of course, is absolutely crucial. Grapes is a fruit, when you pick them, that's it. They will not ripen anymore. Like some fruits, they keep ripening after you pick them. Grapes won't. Now, beer, on the other hand, is a bit different. It has a very complex start because the barley is used to make malt, and that's in itself a very complicated thing. And then the actual brewing is less sophisticated when I compare this to wine. So this diagram, actually I stole it from a website from a company. They make monitoring equipment. So they are inline, these little flags show spots where they sell instruments that give you an idea of the color and the turbidity of the product. So basically the grapes after harvest, the berries are separated from all the stems and leaves. They get that out of there. It's crushed, and then the material is put into a big vat to actually let the skin settle. And what you get then is the must. So must, German word is Most with an O. That's basically the juice. And there's free run must. And then if you squeeze the skins, you actually get more must out. Sometimes that is used to make a separate wine. Obviously it will be a little bit different, or is simply added to the juice in one big batch. And then comes the fermentation. So yeast is added, and of course, back in the days, the yeast is everywhere. There's natural yeast on wines, on the grapes, and so they will start the fermentation. But of course, today, a winemaker can choose a particular yeast and control that process. I'll tell you a little bit about sulfur dioxide, which is used long history to prevent bacteria from spoiling the whole thing. So fermentation then goes on to produce the alcohol, and of course now I have large numbers of yeast cells growing in there, which eventually I have to remove, which is done by filtration. So we remove most of these organisms, and then we start the long process of maturation. In fact, let me quickly go forward one slide, because in this scheme they leave one step out. After the fermentation by the yeast, there is a second fermentation by bacteria. And those are crucial. What they do, they take malic acid, which forms by the yeast, converted into lactic acid. I'll tell you in a minute why that is important. Wine wouldn't taste as nice as it does if we skip that. So then there's a lot of further processing. The filtration still makes a product that is cloudy and unappealing to look at. And of course, there's always some flavor in those cloudy-making materials. So fining agents are used to absorb those particles. For example, one that is commonly used, this word here is basically, it's actually German, although the whole thing is in English. Silicon dioxide, SiO2, is a very fine powder used for all sorts of purposes. It's the skeleton of diatoms, aquatic organisms, and it has a very high absorbance property, so it will simply cling to all the debris in the wine and then ultimately give you a very clear product. And there is still more chemistry going on after all this as the wine is stored in various types of containers. So that malolactic fermentation, two problems if you don't do that. Wine can spoil. There's always bacteria lurking that can make it into the product, and if they do, and there's still malic acid left, they'll go to work. That's their food. And then they produce chemicals that spoil the wine. Second, malic acid has a strong flavor, and most people don't like that sort of flavor. So by converting it into lactic acid, which has a very weak flavor, you solve that problem. So then in essence, we have the alcoholic fermentation by the yeast, and then the malolactic fermentation by the bacteria. There's actually wines, most reds and some whites are subject to the malolactic acid fermentation. So actually many white wines, this step is omitted for the purpose of flavor. Now the sulfur dioxide story, like so many things, were discovered by serendipity. The Romans used candles to work in the winemaking cellars, and they noticed when you have the candle going, you get better wine than if you don't. So and they noticed, I'll tell you in a minute, the metabolism of wine, of alcohol, goes from ethanol to acetaldehyde to acetic acid in our metabolism. And acetic acid is vinegar. It smells very strong. And they detected that, and they noticed if you use this, what we now know as sulfur dioxide gas, it prevents this. So it's an antimicrobial action, and it's also an antioxidant in this business. So in the wine aging, we have to realize you work with a whole organism, the wine, the grape, and then with a whole organism, the yeast. So you're dealing with thousands of biochemicals in their life, and so they produce an array of compounds that are in these products. And well, they chemically change during the aging process, whether it's in barrels or in large metal containers, stainless steel, and so forth, or even a bottle, it continues. So barrels, for example, is a very expensive way of aging wine. This is very particular wood from oak trees, and often they will also be subject to fire to roast them a little bit. And then you put the wine in, and obviously now the fluid will leach out chemicals from these barrels into the wine. So in fact, similar to roasting barley to make malt, here you're roasting the barrels. So you can do a light roast or toast, medium and heavy, and then you get certain flavors. Now this is not my field of science. The description that the sommeliers use to describe this is really not science in the hard sense of it. But anyway, it's obvious that you would affect the flavor by doing this to the wood. In terms of sweetness of wine, when you harvest the grapes, they have a very high sugar content, as we know. In fact, I don't know, most of us probably never eaten grapes that are actually used to make wine, which are a little different from the ones you buy in the grocery store. The ones that are used to make wine are actually much sweeter than most grapes that we eat as fruits. So now, the simple sugars that makes them sweet is glucose, and fructose is the really one that is very sweet. And typically wine, as it's fermented, it's never fermented completely so you have every sugar gone. So the residual sugar will determine how sweet the wine is, basically. So at harvest time, glucose, the amount concentration at the bracket, equals fructose. Grapes that are overripened, then actually glucose is less common than fructose. So it's actually sweeter. And then, of course, there are dessert wines. Now, the winemaker, again, can tweak all this. They can artificially stop the fermentation by temperature or add ethanol. So, obviously, this is now, again, a willful manipulation of the sweetness. Just to show you, for example, the color in red wines and rosé, and just the concentration difference. Here's the chemical. For those of you who are a bit familiar with chemistry, here you got a conjugated system of alternating double bonds, and the right picture here shows the absorption spectrum. So the anthocyanins in grapes, they absorb this light here, which is actually the greenish light, and they reflect the other light, which then looks red to us. By the way, chlorophyll is green to our eyes. Chlorophyll absorbs actually, well, UV light, which we can't see, but chlorophyll absorbs blue light and red light and reflects green light. So the chemistry of pigments is always backwards. What they absorb is not what we see. Is what they don't absorb of the white light is what we see. So interesting, there's all these, the literature on is red wine really very healthy for you and prevents heart disease and lipid problems, arteriosclerosis, and all so forth. A little bit, but look, I'm a pharmacologist. We have drugs that do a much better job than this. It is overblown, the effect of antioxidants on cardiovascular disease. It's small compared to drugs. Now let me tell you something about beer. So we are now in the 500th anniversary of the, again, there was no Germany back then, the Bavarian purity law of what shall be in beer. And at the time, they actually did this to keep the brewers hands off wheat, which was needed to make bread. So to protect the bread making industry from the brewers stealing all the grains, they said you can only use barley, water, and hops. They didn't know about the yeast at that time. That just happened by itself. They thought Wotan spits into the vat and makes it bubble. So anyway, in fact, Okanagan Spring has for a long time a beer named after that year. So 1516, that's the reason why they have that beer. By the way, then Budweiser in the United States is actually made, in violation of this, they use about 30% of the carbohydrates from rice rather than from barley. So now the beer making, like I said, it's complicated at the beginning compared to wine. So the barley itself is different from grapes in that it is full of starch. Starch is a long polymer, so the glucose molecules are connected chemically. The yeast would have a hard time dealing with it. So in the wine, it was free sugars, good to go for the yeast. So then how can we solve that problem? If you take the barley and you simply let it germinate like it would in nature. Keep in mind, a barley seed had in mind to grow another barley plant next year and not you to eat it or drink it. So if it gets wet and warm, it will start the little embryo to germinate. So it starts growing. And the kicker is, at that process, the starch in the grain is beginning to be converted to free sugars. And that makes them usable to the yeast. So this is why in the malt factory, they steep it and they let it germinate. And then they say, now you die. Because I don't want the plant to grow and use the nice sugar to make a new plant. I want the sugars. So then they simply use heat to stop that process. And at that stage, they sell it. And the rest then is then happening in the brewery. So when they make malt, let me skip. If you want to read all these slides on your own leisure, they're on the website. I'm limited in time here. So in a nutshell, I told you what the malting does. But here's again what humans have invented then to tweak this. The killing of the malt, it's actually amazing that the enzymes in the malt survive the heating process. So they're tough proteins. So when you heat them, there's actually this guy Maillard, a chemist, who described this first. When you heat anything that has carbohydrates present and proteins, how about a piece of meat? Who would have thought that it has carbohydrates and meat? Of course there is. There's glycogen in muscle, which is a polymer of glucose. And when you heat these chemicals in their presence to above, well over 100 degrees centigrade, there's a chemical reaction called the Maillard reaction that makes brown products. You know, when you throw a piece of meat into boiling water, it just turns into a gray shoe leather piece. It's not hot enough. You need above 100 degrees to cause the Maillard reaction. So that is the barbecue effect, the French frying effect, and it's the same effect that causes the malt to get darker. So, for example, if you have a dark beer, it doesn't mean it's a strong beer. Strong, quote unquote, we might talk about the alcohol content. The color has nothing to do with this. It's merely the barley was roasted longer. In fact, you probably know coffee beans are not dark brown either. They have been roasted. It's the same idea. So anyway, there's lots of temperature profile involved to make the sophisticated product of the malt. Let me leave it at that. There's hard science behind, not like the sommelier with the vanilla and the oak flavors. They use a spectrophotometer. If you want to describe the color of a beer, there it is. They say it has 3, 10 or whatever. And again, rational scientists, I love those people. What they do, they say, okay, this compound of the Maillard reaction absorbs light at 430 nanometers, visible light. They put it in a spectrophotometer, the beer. You don't need much, you don't waste much, you just need a little cuvette full of beer. And you measure the absorbance, and those numbers generally are 0.0 something, 0.12. So they would be difficult to speak about with a brewer. Then they said, let's multiply those absorbances by 12.7. Somebody made this up. And that gives you then numbers that are easier to talk about. Again, for the chemist, Eric sits there. It's the same idea when we invented, or somebody in Sweden invented the pH scale. It's the same thing. It makes speaking about this much easier than if you really talk about the molarity of proton ions. So anyway, the beer color is, obviously here are some of the beers with their appropriate color code. Now to the brewery. So the brewmaster, for example, here our local brewery, you can see all the sacks of malt he buys from Bavaria. He mills then this product himself. Obviously, you grind your coffee beans. The yeast would have a hard time dealing with an intact grain of malt. So they are ground right in the mill and then steeped in water. Now this thing is called grist. And then basically you're starting to extract all the sugars into the liquid. And then eventually, there's a lot of mechanical issues here. You got to get rid of all the cellulose material, and eventually you remove the juice, which is now called the wort, and that goes into the actual brewing kettle. Again, because of time constraints, I have too much information here. Let me bypass this here. Again, there's a lot of chemistry going on in the brewery still. Like I mentioned, the malting process doesn't kill all the enzymes. So by putting in warm water, you again help the yeast to prepare the starch that is still there for fermentation. So in fact, by the time they're finished, the liquid wort is now ready to go. So it is technically called a wort, and it's ready to go for fermentation. Beer, in a sense, is a much more nutritious thing than wine, because I'm grinding up this entire organism. Well, after all, it would have been a whole new plant. So there's a lot of other stuff than sugars in there. There's amino acids in there. There's still intact proteins in there, vitamins, and of course the carbohydrates. Anyway, there's another purifying process. If you ever made beer yourself, there's a lot that can go wrong. And so professional brewers know about all the pitfalls. So Lautering is the old German word for, we don't use it anymore, for eliminating, for example, nasty proteins. It stops the amylase activity, and it makes the mash and wort more fluid for action of the yeast. All of this, I know Daryl too, he has a little turbidimeter so he can measure how cloudy his wort is. Cloudiness always points to undissolved proteins. They look ugly and they also taste bad. Interesting, the word brewing actually refers to one step of the whole process, which is the boiling. So they used to always use copper vessels. Nowadays, I know our brewery here in town uses stainless steel. And so the wort is boiled for an hour to basically sterilize it. You can rest assured there will be bacteria in there, which will foul up the beer. So by boiling it, you will kill most of them for sure. Also, that precipitates more of the proteins which are removed. And also that process empirically has been found to make some grainy flavoring compounds disappear. Actually, some hops are added here. I'll tell you about the hops here next. So it's interesting. Humans are about the only species that don't mind eating or drinking bitter stuff. Most animals avoid that for good reasons, because there are probably alkaloids associated with this taste and they're generally toxic. So, but we know it actually tastes nice and is not bad for us. In fact, there might be some useful medicinal qualities of it. Anyway, the plant that we use, Humulus lupulus, is actually a relative of the pot plant. So it belongs to the same family of cannabis. And we use the cones. So these little cones, in the past, they were just thrown in the brew and they bittered the beer. Today it's a little different. You can imagine again, if you just throw this whole plant piece into your brew, a lot of material won't get extracted. So nowadays, I know Daryl at the brewery here, he buys ground up pelleted hops, which again make the access to the compounds much easier. In fact, you can even buy extracts that are made by liquid carbon dioxide to preserve. You could use heat, like when you make coffee. If you use heat extraction, you would ruin some of the delicate flavoring agents. Liquid carbon dioxide wouldn't. So then what's in the hops? Again, this is a little bit of a chemistry lecture too. There are two things, resins and oils. The resins are so-called alpha acids. In fact, the chemist would see this as a very interesting vinylic carbonic acid, so it's kind of an interesting structure. So those give the bitter taste. In fact, we have receptors in our mouth, not in the nose. You can't smell bitter things, you can taste them. So we like that. And of course, the more you add, the more bitter the beer will be. And then the oils, that's hard to describe. That gives the beer a certain hoppy nose, whatever that means. There's no science to that word again. And to me, they're interesting. The compounds in the oils are hydrocarbons, meaning there's only hydrogen and carbons. And if you got nothing better to do, if you count the carbons, there are 10. There are 15. And that reminds me of the whole family of thousands of terpenes. So terpenes are all made in the same biochemical pathway. You and I, we make terpenes of this kind. We make cholesterol. It's a terpene with 30 carbons. It's fascinating. They're like tinker toys. Terpenes always are made from building blocks of 5. If you have 2 5s, you have 10. That was the compounds in the hops. If you have 3, that's a sesquiterpene. If you have 20 carbons, that's a diterpene, and so forth. And I'm sure you're familiar with most of these chemicals here. Geraniol is an odor that we associate with geraniums. It's a terpene. Limonene, menthol, thymol, that one doesn't smell because it's a baked terpene. It's a compound that is used in cancer treatment. Retinol in carrots, lycopene in tomatoes. They're all from the same class of chemicals. So anyway, just a little aside, there's more. So then when it comes to the bitterness of beer, I spared you the slide. Here it's actually not done by flavor, rather there's a formula that says how much hops was used to make beer, and there's a simple, a complex calculation that says the bitterness is this number. So, and then of course, as you know, if you are a beer drinker, some beers are very mild. Now I'm using the word mild to say not bitter. And then how about pilsners? Typically are quite high in the bitter scale. So now the actual fermentation, of course. So where was I here? Fermentation. So now we made the wort, it's boiled, sterile, and now we add in the yeast. So the fermentation, now the hop wort is cooled and pitched with the yeast, and then they go to work. And now, of course, today we have all these sophisticated distinctions between ale strains, lager strains, and the traditional ale and the traditional lagers. Again, for time reasons, let me not go into the detail. I'll give another lecture soon in the brewery. Well, it will be an hour and a half only about beer. Then I have more time to go into the details. So, but let me just tell you a couple of things about fermentation. So obviously, similar to wine, the yeast is going to work. And again, there are big temperature differences, like ales and lagers use a very different temperature. The yeast multiplies and generates heat at first, and then the actual longer fermentation in which the alcohol is produced is run at very different temperatures depending on the type of beer, and also that will determine whether the yeast is at the bottom or at the top. Just like in wine, when I make when the fermentation is over and I have green beer, it tastes awful. And one chemical that causes this awful taste is a diketone called diacetyl. Interesting, the thing in the wrong place is ugly. If you put it in the right place, like an ice cream, we say that's nice. It actually is the typical flavor of butterscotch. So this chemical smells, you can't taste it, it's all smell. But when we eat things, most of the sensation comes from the odor around, not the actual chemicals in the mouth. So, and in beer, this is no good, so we want to get rid of it. And by letting the fermentation carry on a bit more and all the CO2 comes out, this chemical is volatile, so it will evaporate and disappear. And then the skunky taste is gone. Anyway, the condition and carbonation, obviously, what's the bad? The worst beer is no beer. The second would be flat beer or warm beer, maybe equally bad. And then, of course, fresh carbonated beer. So praise to the guy who invented this carbonation process. Let me just tell you here, the carbonation of water was actually invented by Joseph Priestley. He was quite a chemist, and in those days there were still scientists on all levels of physics, chemistry, and so forth. And then a guy in Switzerland by the name of Schweppe, he industrialized it, and we still have the company of Schweppes where they make tonic water. So then the beer brewing, of course, naturally made carbon dioxide anyways, but now it was done sophisticated and kept carbonated. Interesting, oxygen is an aggressive chemical and you have to keep it out of beer. So, and not too long ago, I don't know if you remember, Kokanee had a sales gimmick a few years ago. They invented a cap that's supposed to have a chemical in it, it probably did, that will bind oxygen so the beer lasts longer. And of course, there was a lot of jokes. So who needs a cap like this? The beer lasts long enough for most people's consumption period. So anyway, also beers, after all, it's a liquid and it's food and it can spoil. So big breweries actually pasteurize the beer for preservation. Our local brewery doesn't, so beer has a limited shelf life, even when you don't open the bottle. Anyway, final, we have the product here. So for time constraints, let me just tell you a bit about not all the complicated chemistry in there. The nutritional aspect, very different. Wine has really just alcohol, water, and depending how sweet it is, sugar. Beer is very different. If you take a 6-pack of beer, you would have in there 540 milligrams of potassium. 3,500 milligrams is the daily recommended intake. Recommended daily intake, that's what that means. 80 milligrams of calcium out of the 1,000. 280 milligrams of magnesium. In beer, there's 10 grams of protein in that 6-pack. So, I made a little asterisk. That is why beer foams and has a head. Proteins accommodate air bubbles, whether it's CO2 or air, in a foam that's somewhat stable until you put grease in it and it collapses. That's why wine wouldn't foam. Finally, of course, there's some unfermentable carbohydrates. In fact, as gimmicks again, you can buy low-carb beer, where the industry found a way to get rid of these. And beer, of course, in that sense, is similar to wine because of the alcohol has so many calories. A six-pack like this would have 820 calories, which is quite a lot, considering that we need only 2,000 per day. So anyway, look, my picture of the six-pack. So if you drink enough beer, because of the caloric content of beer, the idea of a beer belly is very justifiable. So of course, if you exercise, you might drink your beer and still have a six-pack. So it's all a matter of what goes in, what comes out. The caloric expenditure will make an effect of the beer belly. Now let me briefly say something about hard liquors. So let me skip the history because I want to keep in my time here. So people have invented a long time ago that when you heat a mixture of alcohol and water, basically beer or wine, those kind of things, if you heat them, because alcohol has a boiling point substantially lower than water, the vapors are enriched with alcohol. So if I catch them by condensation, I can purify or concentrate the alcohol. So that's what people did. So then distilled spirits, they use, of course, a more sophisticated fractional distillation, and most of them are kept at or below 40% alcohol, so more than triple like most wines. Then there's a lot of storing again involved. All distillates are clear. So real distillation products have no color. So whenever a hard liquor has a color, it comes from somewhere else. For example, of course, whiskey is the color of the barrel that it was aged in. So is brandy. Or this stuff here, look, it's all chemistry. There's just food coloring in there in the curacao for making a blue Hawaiian, right? Distillates never have a color. So of course then the equipment, it all depends on the scale. Of course industrial production nowadays uses again stainless steel. Here's an old-fashioned smaller scale copper equipment. So there's even a way to make hard liquor by freezing. The Applejack is an interesting method where you simply take fermented apple juice, which is like wine, and just put it outside in the winter, and as it freezes, the top layer is not freezing as uniform the concentration of the alcohol water mixture. So there's actually more water you remove when you chop up the ice. So you can actually reach concentrations up to 40% in the Applejack with this. Anyway, then of course people have made moonshining. In fact, it's interesting. Why is that illegal? You know, you can make wine and beer, so you can make alcohol. The government lets you do that. Why don't they let you moonshine? The reason being, when you start distilling, you might enrich methanol, which is toxic, very much more toxic than ethanol. Also, when the prohibition was on, people used all kinds of materials and equipment where they poisoned themselves with metals, with solvents that were in those machines before they were used. So I love all these words. The home distills, they have these flamboyant, well not flamboyant, interesting names, of course, moonshining, white lightning, Mountain Dew, hooch, homebrew, and so forth. And so anyway, during the prohibition, like I mentioned, lots of stuff went wrong. And I know a thing about moonshine because I used to play in a band. I don't know if you can recognize me. This is about 18 years ago when we looked all a little bit younger. And that was certainly a band that was fit to the name, I can tell you. We played bluegrass, of course. So now, distilled beverages. Let me skip the history and just do a quick overview. What's the difference between all these things? For example, whiskey. St. Patrick's Day coming up, right? So obviously was invented in the UK, and it's made from barley, so pretty much like beer. So the carbohydrates in this product comes from the barley plant. Now gin is an interesting one. It's flavored by adding juniper berries, which are very strong, peculiar flavor, and they're thrown into the distillation process, and thereby you extracting all these goodies from those berries that go into once more clear liquor. Brandy, the word comes from the German word Brandwein, so literally burned wine. So it's made obviously from grapes. And the color again from brandy comes from storing them in oak barrels. Vodka actually is one of the cleanest things you can buy because it's not stored in anything that gives it any flavor. So it's straight distilled stuff. In fact, most is done from sorghum, corn, rye, or wheat. But also the Polish people, they seem to have used everything that is fermentable to make vodka. Tequila obviously is a very unique product from the agave plant, and again, if you read all this on your own, again, you have a very hard plant where how does the yeast get access to the fermentable material? So there's a lot of procedure involved in making it fermentable, and then also then manipulates the flavor. Again, when you distill this in the end, tequila has no color. If it has a color, it was again stored in some form of container. I was in Austria a couple of years ago, and I learned, I didn't know that, the word schnapps that we use here is actually pretty low-grade material. When you look at this, in Germany and Austria, they make something called Obstler. Obst means fruit. And look at this, the top end, Edelbrand, means a noble distilled or burned stuff. They use basically 100 kilograms of fruit, for example, plums or cherries, and you get 6 to 12 liters of this distillate. So all the alcohol comes from the fruit, and of course all the other chemicals will be in this. Grappa even gives you less if you use that method. And then the lower grades, you can see when you come to schnapps, there's only a third of plants, and then this goes down to 5%. The rest is all industrial alcohol. Now let me just finish this off if I can, 5 minutes. The problem of alcohol. Now alcohol, of course, as we all know, we've been around, is a component affects the nervous system. There's acute and chronic effects. The acute ones are very obvious. Interestingly, people at first become euphoric, and that makes them be more risk-taking behavior. Some people let out their anger. Isn't that interesting? As long as we're sober, we keep some things to ourselves. And when people are no longer sober, now you really hear what they think. And I think that's where some of the aggression comes from. Many chemicals, the alcohol itself, and all the other stuff in liquor or whatever we drink that is not ethanol, they're called congeners, like the phenolics from the barrels. All those can make you sick. If you have enough of this, they're all toxic in their own right. And many of those, the combination will make people throw up. We have nice words for throwing up, emesis, right? Then of course people, when they're drunk, motor coordination is not working, they fall, they have accidents of all sorts. If you keep drinking, eventually the real sedative effect of ethanol is obvious, and people start falling asleep or become even unconscious, which the difference is you can't wake them up. And that's a good thing, because in theory you can kill yourself with ethanol, because it will cause respiratory arrest like opiates do. But normally you have passed out or thrown up before you reach that. So typically death is not a result, but it could be. Then of course the chronic problems. I don't need to tell you about social, financial problems. If you drink enough, you're almost guaranteed a fatty liver disease. You might get liver cirrhosis. About 20% of chronic alcoholics get that. And you might even get liver cancer. And acute pancreatitis, a very nasty disease, is associated with alcohol consumption. There's also long-term damage to the brain. Interesting, both of these, Wernicke and Korsakoff encephalopathy, are actually vitamin B deficiencies. So if you were to actually take supplements as an alcoholic, and of course they're not cohesive enough to do that, you could prevent that. It's merely a nutritional defect. People that are really alcoholics, they get all the calories from booze. They don't really need to eat much. Hence the nutritional problem. It's a bit more complex. And then of course I have to put one more nice quote in here. Erectile dysfunction. Shakespeare had already said it provokes the desire, alcohol that is, but it takes away the performance. So I learned this in my high school from Sister Mary. Moderation takes care of everything. Anything in bad concentration is trouble. Now let me just finish off with some of genetics and pharmacokinetics. So alcohol really is a nutrient. The reason why I say this, if you take an ibuprofen, this is a foreign chemical. Of course, it has effects on my body, but the liver makes it into something that's more water soluble and you pee it out. Alcohol is different. Alcohol is a nutrient. You can completely burn it to get calories out of it. And so you need two enzymes to do that. Mainly they're on the liver. So the alcohol dehydrogenase takes the alcohol and converts it into acetaldehyde. The chemists can see if you look, there's two hydrogens missing, hence it's called dehydrogenase. That gives you energy. Then the acetaldehyde can go either in the mitochondrion or stay in the cytosol of the cell, and regardless, it will then convert it another time by an enzyme called aldehyde dehydrogenase, another oxidation which gives energy in form of ATP. And now we are at the stage of acetic acid, and that is run through the Krebs cycle to give you the enormous amount of energy. So hence, it's a nutrient, and that's why it has so many calories. So carbohydrates and proteins have 4 grams per calorie, 4 calories per gram. Alcohol has 7, almost double. Fats have 9, so it's just outdone by fats. And here's some interesting genetic differences in people. Half of the Japanese population have one nucleotide in the gene that encodes the second enzyme. So one nucleotide in the gene, in this case it causes one amino acid from glutamic acid. They have a lysine instead. You can tinker with biochemicals. If you do, in this case, that enzyme is 500-fold less effective as a normal enzyme. So that explains why these Japanese people don't like alcohol. Because what happens is when they drink alcohol, they convert the alcohol into acetaldehyde. Any other person then, in sync, processes the acetaldehyde into acetic acid, and off it goes. In the Japanese people, about half of them, the acetaldehyde accumulates because the second enzyme is too slow. So it's out of sync. And acetaldehyde is a bad vasodilator. It makes your blood vessels dilate and you blush, and you might even get a headache, so it makes you feel very uncomfortable. Typically, people like this don't enjoy drinking because it makes them feel miserable. In fact, when I studied pharmacology in Germany, my professor taught me this many years ago. I can read it for you. Abhorrierende Alkoholentzugstherapie. So translated, it would mean horrifying alcohol withdrawal therapy. Basically, you can make yourself a Japanese genotype by this drug called Antabuse. So you take the pill, give it an hour, and then you have 1 glass of wine and you feel miserable, like the Japanese, because you artificially block the enzyme's action. I'll give you one last example. In southern China, actually in the far southeast of China, here is an interesting story. Those people have an alcohol dehydrogenase, so the first enzyme dealing with alcohol. They have a mutation again. One amino acid, arginine, is replaced by histidine, and their enzyme, their first enzyme now, is between 40 and 100-fold faster than the second enzyme. So the effect is the same. They don't like alcohol because they make so much acetaldehyde, it makes them sick. And now look here, go first to this slide here, go back. In genomics nowadays, people sequence all kinds of people. So when you sequence the people in this area of southeastern China, 100% have this alcohol intolerance. And as you can tell, when you go away from this area, the number changes to basically what we are. So the question then is, what happened there? Why is this? And there's ways in molecular biology, molecular genetics, you can date how long ago this mutation has occurred. Our species is about 200,000 years old, so 7,000 to 10,000 years is a small time period. So then the question is, Where are the original humans here that had different gene? Where did they go? The theory is, and of course, how do we know whether it's true? The theory is, this is the same time when the Chinese, that's what these symbols talk about, invented the domestication of rice. So they were producing a very carbohydrate-rich crop, which then must have probably made them discover, oh, you can ferment that stuff, and they made alcohol. And I can only, well, the scientists only assume the people that indulged a bit too much in alcohol, because now it was available, didn't do so well, and they were all replaced by the people that didn't drink. I could give you the same example about lactose intolerance in Northern Europe. Same thing. If you go to Finland, if you don't count the immigrants, but the original Finns, they would be just like that. They're all lactose tolerant, while actually intolerance was the original Homo sapiens genotype. Where did all the Finns go that had the original genes? Well, we don't know. They're extinct. So, what about North America? Some people think that First Nations are prone to alcohol problems, and there's some genetic reason. That is not so. Prior to contact with colonists, alcohol use and production was very limited to the southwestern US. So the history here in alcohol use is very short. They had some wheat beers, wines, and so forth. And mainly they were used, like everywhere else, for the most part, for ceremonial purposes. There was no heavy drinking at all. Then, of course, the white people come over here in the colonial period. Europeans brought large amounts of alcohol. There were some practical reasons. Beer and wine was safer to drink than water, because water often was contaminated, people got sick. So the Mayflower actually brought more beer than water for the workers, for the sailors, for many reasons, and so they brought a lot of alcohol into North America. And then alcohol, then of course, people like it, and the natives liked it too. So it was used to trade. And then of course, there was a lot of cheating going on. Early traders then caused a large demand for alcohol. And then read this here, the traders giving free alcohol to Native Americans during trading sessions. Obviously, they got them intoxicated to cheat on them, right? So not very nice practices. So the question is there some genetic problem with the First Nations? And there isn't. So, by the way, when people talk about ethnicity, and often I hear there's an ethnic background for this and this disease, we call this in my field pharmacogenomics. Simply, ethnic groups, of course, share gene pools. That's what it is. So basically, there are a lot of genetic links to all sorts of diseases. I study this for a living. It's very complex. For example, high blood pressure, obesity, depression, schizophrenia, they are not single gene diseases. That's different. There are many of those. They are complex, multifactorial, so you need lots of gene combinations to cause that problem. Often we still don't understand what they all are. Slowly we're picking them apart. So recently there was a review of the literature looking at the question, do American Indians actually have a different gene pool that explains why they might be more vulnerable to alcoholism? And it's not. There's a substantial genetic component in Native Americans, but that these factors are similar in kind and magnitude to the genetic influences contributing to the liability for those phenotypes in other ethnic groups. So that was published in the American Journal of Psychiatry. Basically, all ethnicities around the world have people that like to drink and are prone to become alcoholics, and others absolutely don't like to drink. And we know very little why that is. One culprit for sure is the dopamine receptor in the brain, which is involved in pleasure. There are different variants of them, and that's probably one link why some people just don't like to drink and others like it very much. And this is where the problem lies. And it's not unique to our First Nations. It's found in any ethnicity. Sorry, I went over a few minutes. Thank you for your patience.
Small token of our appreciation here. I'm sorry it's not a full bottle, but it is a hiking bottle. I'm afraid I have to run off to another meeting, but perhaps John can stay around and answer your questions.
Yeah, I'm happy to, if I can, answer any question that you might have. Go ahead.
Is the alcohol limit in beer, is that because of the heat?
I couldn't hear. The alcohol limit?
Like most beer is 5 or so percent. Is that because of the heat, or why does it not have 15 or 20% alcohol in beer?
Well, there are strong beers. There are beers that have 12%. The yeast can handle 12% beer. Just its desire. Obviously, if you make very strong beer, you would have to drink less, or else you become too quickly intoxicated. Another interesting thing is the higher ethanol inhibits antidiuretic hormone secretion, which means alcohol dehydrates you. You pee more. When you drink beer with 4% alcohol, you drink 96% water. It fills in the void. It's like you're losing water by urinating more, but you fill it up with the water. If you drink strong beer, for example, 12% beer, now you have only 88% water, so you dehydrate more. And wine, of course, and then hard liquor is worse. I think it's just choice. People like a beer that has 4 to 5% alcohol. Yes?
I've recently been doing some research into the Incas, and they made a corn beer called chicha. And from some of the reading I've been doing, the women who were charged with the task started the fermentation by spitting in the must. Is that possible, or is this just baloney?
People do things, like I mentioned, the Germans thought Wotan, their god, spits. Well, the Germanics thought that something happens why this all of a sudden starts to bubble. And we humans, okay, let me put it this way, yeasts are everywhere.
Yeah.
You will have yeast in your mouth, for sure. In fact, we know that if you're treated with strong antibiotics, which kill bacteria, yeast is a fungus. Antibiotics do not kill fungi. So sometimes people get oral thrush, that's a fungal infection in their mouth or vagina. It can happen because you're eliminating the competing bacteria. So it's possible, but I'm sure it's not necessary. Have you ever had food that you leave on your counter long enough that doesn't get moldy?
Right.
The fungi are everywhere. They're actually even more abundant than bacteria because of their spores. They're very hardy. Go ahead.
You mentioned one of the problems with backyard distilleries is the methanol content.
Yes.
Wasn't there something also involved with copper?
Oh, there's
chemical reaction with what you're trying to distill?
Copper is actually fine, but people welded stuff together from, I had it on my slide, they used car radiators as a cooling device. So then there's metal, heavy metals leaching. Copper is actually not that bad. It's lead and other materials. But then the methanol. The problem is when you have bacteria contaminating your beer or winemaking, they will be, by the methods, far outnumbered by the yeast. So, and it's interesting pharmacologically or toxicologically, when you have a lot of ethanol and a little bit of methanol, the toxicity of methanol is negligible. It has to do with the alcohol dehydrogenase will work more on the ethanol, and methanol is not toxic. The formaldehyde that's made by the enzyme is toxic. So if the enzyme is busy with ethanol, it will oxidize the evil methanol to formaldehyde very slowly. But when you distill and you have some methanol and you make a big batch of moonshine, one of the bottles, if you don't know which fractions to throw away, would have most of the methanol, whereas others would be nice and clean. So, and of course, if you had a gas chromatograph, you would know, oh, we had a contamination with bacteria, we have methanol in our product, but I know where it went because I could measure it. But of course, that's not what they do. So then people, methanol is very different from ethanol in its toxicity. The retina and the optic nerve is very sensitive to that. So it's true, you go blind. And that's the minor problem. You will die, like you ruin all kinds of tissues. Formaldehyde is a very aggressive chemical made from methanol. Go ahead.
John, I have a question about ciders. Where do they fit in between, I mean, is it a separate process, or is it closer to winemaking?
Be closer to winemaking, right? It's made from apple by definition, and it's fermented and it's left at a very low alcohol content. I think they generally have 7%. And it's really nothing peculiar about it. Obviously, it's far less sophisticated than making wines. I actually went in Austria. I went to a hotel, and it's run by a hotelier who's also a sommelier, you call it, right? And of course, winemaking is an art. There's so much that can go wrong, and a good winemaker recognizes that the complicatedness of the process, the art. And I know there's an American winery, they try to take the arts out of it, to basically standardize everything you do, like we do in science, to make sure if I had a wine this year and you like that very much, well then how can I reproduce that next year and in 10 years? So you gotta document everything you do as scientifically as possible. And some operations do that. And you can even push it to a point when I think about the description of how wines taste. I mean, you always say it tastes like that because I have no words to describe it. I teach physiology, right? You have only 5 receptors to taste anything, but we have around 350 versions of odorant receptors in our nasal passages. And they are said to be promiscuous, meaning, so it's a receptor protein, and the promiscuous in this business means a molecule might fit very snug and excite that cell like crazy. So it's firing now neuron signals to my head, say, hey, I'm smelling something. Another molecule might fit loose and it excites the cell half as much. The signal now is less. And then the same chemical from my wine might bind to another receptor of the 350 versions that we have. So basically what you have a symphony of these receptors. Some are quiet, some are firing like crazy, some fire a little bit. And your brain then computes, and then he says, oh, this grew on the southern slope, it's a Bordeaux, et cetera, et cetera. In theory, and this somewhere you didn't like me to say it to him. In theory, we could invent something where we clone all these receptor proteins onto a membrane, we waft the aroma of the wine over them, and we record on a recorder the symphony of receptor activity, and then you can say, this wine has so many similarities with that one because look at the spikes of which receptor is firing. In theory, you could do that. I don't think they want to do that because it would take the art out of it, right? By the way, a dog has 1,200 of these smell receptors. I'm not talking quantity, that's the diversity. Of course, you have millions of them, but I'm speaking of the types. So there's a lot of things a dog can smell that we can't. So they're a little better than us, and many animals are.
Does ozone kill fungi?
I don't know. I know ozone is used to kill bacteria, but I do not know if ozone is an aggressive chemical.
Yeah.
It might, but I don't know.
Well, in the big wineries, if they get wild yeasts infecting into their barrels and so on, there are companies that come in and seal off the building and pump it full of ozone.
Then it must do it, or else it wouldn't do that.
Okay. Well, that's great.
If there's no questions, the host is not here, so I'll be the host, and thank you for coming. And again, if you want to read through the slides, Alex has put them on the UNBC website.
Super.
Okay. Have a good afternoon.